Okay, so let's talk about Leetcode number 4, finding the median number of two sorted arrays. So given two ascendingly sorted arrays. So for example, we have array 1 with numbers of 1 to 4, and we have array 2 with numbers of 3, 5, 6, 7. So if we put all the numbers in these two arrays into a single sorted array, which is 1, 2, 3, 4, 5, 6, 7, and the median number will be 4. So we can obviously see that the simplest solution would be to merge these two arrays into a single array, and we can easily find the median, which has a complexity of O of n. So however, the question asks us to improve to a log n complexity. So let's abstract this problem a little bit. Let's say we have two arrays. One has a length of n1, and the other one has a length of n2. So as we want to find the median number, ultimately we want to divide all the numbers in these two arrays into two equal parts. So let's use k to define the size of the first half as part of the division. So k will be equal to n1 plus n2 plus 1 divided by 2. Note that the plus 1 here is to accommodate the fact that when n1 plus n2 is an odd number, so that the first half would contain the median number already. So the k numbers in the first half could be drawn from either the n1 array or the n2 array or both arrays. And m1 will be the numbers we want to draw from the first array, and m2 will be the numbers we want to draw from the second array. With this setting, we can binary search m1 from 0 to n1. So let's derive the basic logic of the binary search. As the search space of m1 is from 0 to n, we define a left and right pointer points to 0 and n1. We do the binary search while the left index is less than the right index. As we always do in the binary search algorithm, that we search from the middle of the search range and we repeatedly reduce the search space by half. We compute our m1, which is equal to L plus R divided by 2. And m2 equals to K divided by m1. One important detail to note is that the number at index of m1 is not one of the numbers that are drawn to be part of the k numbers. Instead, it forms a boundary such that the numbers from n10 to n1, m1 plus 1, are part of the k numbers with size of m1. And similarly for m2. So if the number at index m1 in the first array is smaller than the number at index of m2 minus 1 in the second array, it means m1 will be found in the second half of the search space instead. So we update the left pointer to be m1 plus 1. Otherwise, we update our right pointer to be m1. Let's say we have run our binary search algorithm and we finally got our m1 and m2 value. Remember, our goal is to find k numbers in the first half as part of the division. And the binary search gives us the boundaries for the numbers that we can draw from the first and the second array to make up for the k numbers. So when n1 plus n2 is an odd number, meaning the median is actually the k's number, recording that the median is already included in the k numbers, so the median number is simply the last number in the k numbers. Similarly, when n1 plus n2 is even, the median number is simply the k's number plus k plus 1's number divided by 2. So the k plus 1's number is simply the minimum number of the m1 number in the first array and the m2 number in the second array is the k plus 1's number. So let's take a look at the code here. So we have this find median sorted arrays function that takes in two arrays. And first we calculate the size of each array. So note we have a little trick here that if the size of the first array is larger than the size of the second array, we reverse the arguments. The reason is that we want to make sure the size of the first array is smaller or equal to the size of the second array, which keeps the search space of the binary search small. So here we calculate our k, and here we define our left and right pointers that points to 0 and m1. First, we calculate the m1, and m2 is simply k minus m1. And we compare the m1 element in the first array with the m2 minus 1 element in the second array. If it is smaller, it means m1 exists in the second half of the search space, so we advance our left pointer to be m1 plus 1. Otherwise, m1 will be in the first half where we set our right pointer to be m1. By the end of the binary search, we have our final m1 and m2 value. And the final answer depends on if n1 plus n2 is an even or an odd number. If it's an odd number, we simply return the case number, which is the maximum number of the m1 minus 1 in the first array and m2 minus 1 in the second array. Note here we handle the edge cases that when m1 or m2 is less or equal to 0, it means none of the numbers in that array are drawn to form the k numbers, so we simply delegate to int min number. And if n1 plus n2 is an even number, we calculate the k plus 1's number and sum it with the case number divided by 2. Note here we again handle the edge cases. It means the whole array, either n1 or n2, are drawn to form the k numbers. So similarly, we just delegate to int max. To summarize, in this problem, we used binary search to find the median of two sorted arrays. The binary search is simply to find the m1 index in the first array that identifies the first m1 element in the first array, and the k minus m1 element, which is m2 elements in the second array, that forms the k numbers, which is the first half of all the numbers from n1 and n2. If n1 plus n2 is an odd number, we simply return the last element of the k numbers, which is the case number. If n1 plus n2 is even, we take an average of the k's and the k plus 1's number,